Yeah, the HDMI cables are broken for the past 2 days using the VGA cable. Test. Can people on Zoom hear me? Anyone on Zoom hear me? All right. Wednesday? What did we do on? We did midterm 2 review on Wednesday.
Did we do tries?
Yeah, we also did tries.
Okay. I'm just doing sorting. Okay.
I'm gonna go use the restroom. I think I know why. Because maybe like well, you could have done it 2 ways. Once I asked.
All right. Good afternoon. How's everyone doing? How's the midterm? False? Decline to answer. Huh?
This is a hard midterm.
This is a hard midterm?
Yeah, it's much.
Yeah, that happens every semester. Uh, did I what? Ah, did you complete the midterm or were you completed by the midterm?
Latter.
I'm glad to see that the midterm managed to complete your life. Your life was missing something, and having that midterm completed it. All right. Anyway, we have Project 2B and Homework 3 that are due tonight. After that, it's finally over. You don't have to worry about 61B for a small amount of time. The next thing that's coming up is Project 3A, which is due 2 weeks from now. So you get a bit of a break after today. Almost there. Almost at the end of the big, crazy 61B week. Yay. All right. We should be trying to get the midterm grades out, hopefully within the next few days. We'll figure it out exactly, but we're at the very least going to be grading over the weekend. So we'll let you know further when we get it finished. All right. Before I start, does anyone have any questions? Yeah. Can you make the final easier? No comment. Did I write the midterm? It depends on what you mean by did I write it. So each question was written by someone else, right? So I wrote a few of the questions. Other people wrote other questions. I will say I didn't personally write the hardest one. The hardest question. Yes, I did write the asymptotics one. But it was a teamwork. We all like agreed that this was a good set of questions. So if you want someone to blame for the exam being hard, blame me for it. If you want someone to say, yes, this question was really good, talk to the TAs. They wrote it. Yeah. We'll discuss that later. You can talk to me after a class. All right. Let's get started with today's topics. So now that we're done with midterm 2, we're in the final phase of this course. So we've gone over how to use Java. We've gone over a lot of different data structures. This last part's going to be focusing more on software engineering and algorithms. So we'll be having 2 kind of parallel sequences of lectures in this set. The first one is our algorithm sequence, which will cover basically the sorting algorithm, the sorting problem over the course of 6 lectures. And then we'll have 4 software engineering lectures where we talk more about how you write programs and how you act as an engineer in the real life. We have this optional textbook by John Austerhaus, A Philosophy of Software Design. That's what the original software engineering lectures were built on. We've since modified them slightly to use more like industry experience. We'll see exactly how that pans out this semester. But yeah, in fact, our first software engineering lecture is going to be this Monday. I believe we're actually going to have a guest lecturer coming in. One of your TAs is going to be running the lecture for that. So that's something to look forward to on Monday. It's also an optional lecture, so you don't really have to worry about any of the or about like studying for this on the exam. Who did I say the guest lecturer will be? I don't remember who it was. It's either Teresa or Vanessa, I think. But yeah, one of your TAs is going to be guest lecturing on Monday, I believe. For this part of the class, you'll only have one assignment, project 3. And this project is build your own world. Your goal is effectively to build a video game, and we are giving you no starter code. You're going to be making basically a giant project with only your partner to help. It's going to be effectively a software engineering project. Your goal isn't just to write code that works. It's going to be writing code that you can work on and improve and iterate over like several weeks to a month. So you're going to have a lot of time to design stuff, figure out ideas, talk with your partner to determine what you think is a good idea versus a bad idea. It's effectively a lot more like you trying to build something on your own than us telling you to build something and then you just building that thing for us. Just like in Project 2B, the choices that you make at the start is going to have a huge difference in how difficult the project is going to be in the future. If you decide to make your first part haphazardly, just slap it together really quickly, it is going to be a pain to develop in the future. So start early, start with documentation, make sure that you're building things robustly. So for the algorithm section, we'll be discussing the sorting problem. The idea is that we have some items and we want to sort them in order. This is a useful task in its own right. You generally have a large data set, and sometimes sorting it is a useful first step to kind of get a sense of how the data behaves, right? You'll get the equivalent items right next to each other, so you can find duplicates really quickly. You can find a particular item with binary search very quickly. You can convert them into various data structures. Binary search trees can be an example of how you use a sorted list. And it'll also provide some interesting case studies for how to approach these computational problems. As it turns out, there's a lot of different ways to sort a list. And they touch upon a lot of the topics that we've discussed in this class so far. So any questions before you move on about like how the next few weeks are going to go? Anything about project 3, the sorting problem? All right. So we first need to define what a sort is. So first off, an ordering relationship. Do you have a question or no? Just stretching. Just stretching? Okay. So first off, an ordering relationship is going to be a less than operator that fulfills these properties. So the first property we need to have is the log dichotomy. It effectively says that if you have items A and B, either A is less than B, A is equal to B, or A is greater than B. The second point we need is transitivity, which states effectively that if A is less than B and B is less than C, then A must also be less than C. So these kind of make sense from the context of the less than operator, right? If you have these as numbers, then you agree that this is true, right? It's true that for any two numbers, either one is less than the other, or they're equal to each other. And it's also true that if you have three numbers, and the first one is less than the second one, is less than the third one, then the first one must be less than the third one. As it turns out, you can define this to be true for some orderings that aren't quite associated with numbers, but you can still sort them in an effective way if you have these properties. So a sort is effectively a permutation of the items, such that all the items are less than the items that come after them. So the first item, it's the smallest of all of them. It's less than every single item past it or equal to every item past it. The second item is greater than the first item, but less than or equal to the items past it. The third item is less than the items past it, greater than the items before it, and so on and so forth. So here's an example of a sort or an ordering that isn't like the standard ordering that you might think of. The lengths of strings is an example of an ordering here. And we can show that this is true, right? If you have any two strings, it is true that one of them is going to be shorter or longer than the other, or equal length. And it is true that you have transitivity. If you have strings A, B, and C, and A is shorter than B, and B is shorter than C, then A must also be shorter than C. Now you can get multiple different orders for the same set. For example, you have these 4 words, cows get going the. There's 2 different ways you could sort them according to length. You could have the get cows going, or you can have get the cows going. Both of them are perfectly valid ways to sort this list of 4 items according to their length. This is because the and get are considered equal according to the length operator. So they can be in any order relative to each other. So we normally define an ordering relationship using a compare to. In fact, compare to requires these properties to hold. Java states that this is a necessity of a compare operator, and if you don't do that, then it just says that it's not really going to work nicely. So depending on the type of object you're working with, you might get different sorts. You can also choose how to sort things differently, right? This length sorting is one way to sort things. Are there any other ways you can think of to sort strings? Alphabetically? Yeah. Alphabetically is a good one. ASCII value? Yeah, as it turns out, ASCII value will yield the exact same order as alphabetically because the letters are in order internally within ASCII. Yeah. You might also do something weird like, I don't know, semantic connection. Like if you've ever played Semantle, then it likes to sort words according to how close they are to a target word. So there are some other ways you can sort things that are weirder, but yeah, the idea is there's a lot of different ways you can sort things. Now, one final bit of terminology. An inversion is going to be a pair of elements that are out of order with respect to this operation. So for example, here, if we have this list of items, this 8 and 6, they are considered inverted because the 8 is greater than the 6, but it's to the left of it. It's kind of out of order with respect to the ordering that we provide. If you count out, there's exactly 6 inversions in this list: 8, 6, 8, 5, 8, 7, 6, 5, 9, 5, and 9, 7. And there's 55 total possible inversions that could exist in this list. Effectively, there's 55 ways to pick 2 of these items to determine if there's an inversion. So one other way to define this sorting problem is that you're given a sequence of elements with a certain number of inversions, and your goal is to perform some operations, swapping items back and forth, that reduces the total number of inversions down to 0. Any questions up to here? All right. So the performance of a runtime, the characterization so far that we've been using, where we look at the runtime, it's often called the time complexity of an algorithm. So we said that Dijkstra's runtime was E log V, for example. Formally, we would actually say its time complexity is O of E log V. It's effectively the same thing as runtime, just a more formal word for it. Each primitive operation effectively counts as 1 unit of time, in the sense that the time cost is independent of how big the input is going to be. We can also talk about the space complexity of an algorithm, effectively how much additional space gets used by the algorithm. So that's the memory that an algorithm decides to use. So Dijkstra's, for example, has space complexity theta of V because we created a new array consisting of a queue, or the disk2 array, the edge2 array, and then the priority queue has a maximum size of V units in it. So that's a total memory of theta V. We do note that while the graph takes up space theta v plus e, that's generally considered part of the input and therefore not part of the memory that gets used, at least for the space complexity. Similar to how each primitive operation in time is considered one unit of time, each primitive object, a variable or one element of a list or an array, that counts as one unit of space. So for this portion, we are also going to be talking a bit about the space complexity of algorithms, how much total memory gets used by an algorithm. Yeah.
Does an algorithm have to like does an algorithm like recursively have to use as much memory as greater which kind of complexity?
Does an algorithm have to use at least as much memory as its time complexity?
Like recursion, when it comes to like
when it comes to recursion, that isn't really true. Memory and time are relatively independent of each other. You can think of memory as the maximum amount of memory that gets used. Because if you imagine a recursive call stack, like you can imagine that it goes up and down and up and down, right? As you add more like recursive calls. But when you return from a recursive call, you no longer need the old call stack to exist in memory anymore. So it kind of gets thrown away, and that memory space can get reused for another function call. So if you have a recursive function and imagine that all the variables are like constant size, then the runtime is the space complexity is generally going to be proportional to the total number of calls that get taken in the maximum depth call stack. So the longest chain of recursive calls that get called. Because even if you have, let's say, 2 to the n calls because you're having like this binary tree style recursion, you kind of save a lot of memory by getting rid of the calls that you're no longer caring about, the call frames. Yeah. That answer your question, or? All right. So let's start off with our first sorting algorithm. And we kind of covered this, I think, in lecture 6. And this is selection sort. The idea was we'd start off with a list, right? And what we'd do is we look for the smallest item in the list. Once we find that smallest item, we move that to the end of the sorting portion of our list. Then we just recursively selection sort on the rest of the items. So let's see how this works in practice. What is the smallest item in this list? 2. So we find the 2, and then we move it to the end of the sorted portion. So here, this gray area is a sorted portion. The green area is the part that we have unsorted. And then we selection sort the rest. What's the next smallest item? 15. So what do? Take that item, move it to the end of the sorted portion. What next? 17. Yeah, does it matter which 17 we pick right now? Nope. All the 17s are equal, so we could have picked any of these. We'll just pick the first 17 we see, just to make things simpler. So you take this 17 and we swap it out. Next, 17. We take this, we swap it. 17. We take this, we swap it with the 19. 19. We take this, we swap this with 26. 26. We take the 26, we swap it with the 41. We're done, but we don't know that yet. We still have to keep going until the end. So we go to the 32, and then we get the 41. And now, once everything is sorted, we are done sorting, and we know for a fact that we're done sorting. So we've kind of seen this already. What was the runtime for this? N squared. Why is it n squared? Yeah, you take n units of time to find the smallest item because you got to look through everything. Then the next step, you take n minus 1 units to look through everything, then n minus 2, and so on. You get this triangle and you get n squared total runtime. How about the memory use? What's the amount of memory that we use in this algorithm? Huh? How many people are saying n? How many people are saying constant? Anyone say anything different? Well, let's think about it. The list that we sent in as input, that's not counted in our memory, right? We said that the input memory is not counted within our space complexity. That's just to make things simpler. We're looking for the additional memory that gets used here. So what variables or what additional things do we need to include within our code? Huh? The sorted and unsorted portions? We could store those in separate segments. But as we saw here, what we kind of did was we actually just swapped items. And we didn't really need to like have a distinction between the two, right? We didn't need to know where the sorted to unsorted boundary is, but that was just a single number, a single location in the memory in the array. So we could have stored that in a single like numeric value saying we're at iteration 5 here, we're at iteration 6 here, and so on. Any other memory we needed to include? Yeah, at some point we probably needed a variable for the smallest element. We'd probably need another variable to like temporarily swap items past each other, right? If we were trying to swap two items, we gotta have a temporary variable to swap things back and forth. We'd also need a call stack, kind of like those environment diagrams from 61A. You need some like environment to tell you what you're doing in this current function, and that takes some amount of memory. Anything else? Not really. We only really had constantly many amounts of variables. So overall, I would say that this takes theta 1 memory, assuming we did this swapping in place. So overall, this sorting algorithm, selection sort, is going to take theta n squared time and theta 1 memory if we assume an in-place system and we're using an array. Yeah. Huh? It's not theta n because we have n elements in our array, because we're talking about the additional memory that we allocate. The original array was n elements, but that was part of the input. So we don't count that as part of our memory use. Yeah.
Memory if it wasn't swapping.
Would it be theta n if it wasn't swapping in place? Yes, because we would have two separate arrays for the sorted portion and the unsorted portion. And that would actually mean that we have a second separate array that we didn't start with. Yeah. Any other questions? All right. So this seems a bit inefficient. We look through the entire array every time to find the minimum. Can anyone think of a way to improve this? Yeah? Yeah, we could use some type of tree structure. In fact, we do have something that's really good at finding the smallest item amongst a set of things, and that's a heap. So let's try it out. Let's try using a heap for this. So the idea is what we're going to do is we're going to use a heap so that we can get the minimum very quickly. Instead of using theta n time to find the smallest item every single step, we'll insert everything into a heap, and after that, finding the smallest item takes just log n units of time. So that's going to be quite a big improvement. Now, there's a few options. We could use a min heap and then take items from the top, or we could use a max heap and take items and push them at the end of the array. Either way, we're going to get a sorted array. As it turns out, the max heap is going to be better. We'll explain why that's the case in a few slides. But here's kind of how we'll work on it. We'll insert all the items into a max heap. We'll throw away the input array, create a new output array, and then we'll just repeatedly take the largest item from the max heap, put it at the end of our output array, and then just keep doing that until our heap is empty. So let's kind of see how this runs in practice. We start off with this, and we need to turn this into a heap. So first off, I'm going to insert the 32 into the heap, then the 15, then the 2, then the 17, 19, 26, 41, 17, 17. At the end, my heap looks like this. All right, I've just inserted all the items into a heap. What do I do next? Well, first, how long does it take to insert everything into the heap? Let's take a minute or so to discuss with your neighbors.
That'd be great. And you're like, am I right to 32? I don't know if I can. Am I right? Yeah, yeah, for the people, you can just log in, but the number of applicants in it is going to be, if you're starting first, people starting at 15, so you got the first one, it's just, it's going to be order of the second one should be order of one. It would then just be, oh wait, it's not saying that. Okay. Not sure. I think it's logged in. I mean, but I think I say why. Wait, you log in? Can you sort like for like when you sort all in out, you think we can monitor. I was like, that's yeah. I guess it's the same law. I just think yeah. Like every insertion is just more, it's just along the like the height can be approximately like
All right, let's bring everyone back. What do you think the runtime is for this step? Log n? Just log n time to put all of these items into the heap.
Yes, I guess we're wrong.
N log n. Anyone else? How many people said n log n? How many people said anything different? Yeah, I would say it's n log n. First off, it does take at least n units of time to look at every single one of the items, right? And we are doing something for every single item. Each item takes at least or at most log n time to insert into the tree, into the heap. If you do the math, it does end up turning into an n log n total. You have to do kind of log 1 plus log 2 plus log 3 plus log 4. That does add up to n log n total. Yeah. It should be O of n log n. Yeah, because it could be slightly better depending on the order of the items. But it should be between n and n log n at least. Good point. What's the space complexity? Yeah, to create a new heap, you do need to use theta n heap memory here. Yes. So once we've turned this into a heap, what we're going to do is we're going to just delete the item from the max heap and then put it in the right spot. So here we have the 41. That's the largest item. So we put this at the very end of our array, and then we do our heap, and then we do our reheapification. We showed how to delete them in from a heap in the heaps lecture. We're just doing that repeatedly. Once we do that, what do you do next? Same thing. We take the 32, we put it in. Next one. 26, put it in. Then 19, 17, 17, 17, 15, 2. And once we have that, is the output sorted? Yes, we have successfully sorted our array at the end. Huh?
I don't see how this is naive.
You don't see how this is naive? Because we'll get an improved version in a bit. Yeah, but we can do better. I'm telling you, we can do even better. It's naive. There's some optimized versions.
By the way, is nlogn just for inserting everything into the heap at first, or is it for the entire sorting operation?
Well, we only looked at the insertions first and said that part was nlogn.
Oh, okay, got it.
But this next part might also take some time, right?
Okay.
So here's another question. How much time did that second part take? And did that end up being nlogn total? Or was that still, or was it something else? And let's discuss for another minute. All right, let's bring everyone back. So what do you think the total runtime is of this? How many people say it's theta n time? Why is it not theta n time? Yeah. How many people say it's n log n time? How many people say it's n squared? All right. So it is n log n. Getting the items into the heap, we already saw that's O of n log n. Selecting the largest item takes theta 1 time, and removing the largest item takes log n time for each operation, right? Remove min takes log n time. So if we do this n times, then we get n log n overall. It's O of n log n, not theta n log n, because it might be different for different data set.
Is part of the reason that it's O login and not like data login is because whenever you like remove every item, you're making the heap smaller. So what I thought at first is that the order would be something on the order of log n plus log of n minus 1 plus log of n minus 2 all the way to log of 1.
Yeah.
The order of that is, but we know that that's less than n log n. But
well,
a more precise upper bound you can use.
You do have a good point that we say n log n. That is the same as log n plus log n plus log n repeated n times, which could be an upper bound for log n plus log n minus 1 plus log n minus 2 and so on. As it turns out, they're the same theta bound. Log 1 plus log 2 plus log 3 up to log n does add up to n log n, just approximately. We do say it's O though, because removing the largest item doesn't necessarily take O of log n. It doesn't necessarily take theta log n time for a heap, right? It could take theta 1 time if you're really lucky.
Yeah.
And if you, for example, have a set of all duplicate items, then it is going to take only theta n time to complete the heap sort entirely.
That makes sense.
So you could potentially get better than n log n depending on the data set, but for an arbitrary list, you're going to get O of n log n. Yeah.
The theta bound for an operation that takes log n each time and n times is the same as an operation that takes theta 1, log 1, log 2, log 3 up to log n.
Yeah, I'm effectively saying that the sum of log I, where I goes from 1 to n, is equal to theta and log n. Yeah.
Could you argue that this algorithm would then be would expect to be faster than the, what's called the middle sort of one?
Selection? Or a merge sort?
Yeah, merge. All right.
Yeah.
Because this one is only upper bound by n log n, whereas that one is state of bound.
Can you say that this one's faster than merge sort? You can't really. For one thing, we don't know the constant factor on this n log n, right? And depending on your system, it might be faster, it might be slower. As it turns out, heap sort is really, really bad in certain like for constant factors. But it's in a way that's discussed more in 61C. We'll briefly touch it in the future, though. The other big thing is that it uses a lot of memory, right? We had to create an entirely new heap that's theta n total memory. That's a lot of extra space. That is worse in selection sort, but maybe not as big a deal. Runtime does tend to be more important than memory use in modern computing, especially because we have what, terabytes, petabytes of data at times, but we only have so many seconds in the day. And as it turns out, we can eliminate this extra memory cost using some fancy trickery. This is where we can optimize. This is why this is naive. Now let's actually set up a heap sort that's in place. All right. So one thing I notice here is that with a heap, you end up having a bunch of zeros at the end, right? These zeros don't correspond to any actual data. They're just the space that used to be filled with items before we removed the items from it. And on the other side, the output, it also has a chunk of data that's all zeros. It's just this area that we haven't yet added items to so far. They have really no particular meaning. They're kind of just fillers there. So we really don't need to store them. So what can we do? Does anyone have any ideas on how we can save n units of memory? We have a resizing array. I mean, having a resizing array is itself going to take the n units of memory.
We could find a way to insert it the same, because for our heap, when we make it smaller, we're gonna have like some chunks of memory left off at the end. We could find a way to just put it into there.
Yeah.
So,
like, what if this area here, this red area in the heap section, that contained our sorted data? Then we don't actually need to use an extra memory array. We've saved the full memory array. And if we do this cleverly, then we can actually put our heap in our original input space. And if we do that, then we don't even need a second array. And now all of a sudden we use only theta 1 memory. That's really good. So let's do that. This is what we're going to end up doing. We're going to convert the input into a heap somehow in place so that there's no memory extra that's used. And then what we'll do is we'll delete the largest item from the max heap and move it to the end of the heap. Remember how in a heap, what happens is we take the last item in the array and swap it with the root? As it turns out, that's exactly what we want here. We want to take that largest item and swap it with the last item in the array already, because that's where it's going to end up in the sorted array. So we just do that. And if we do this, then we should end up having no additional memory cost. This is entirely theta 1 memory. It's in place. So our first step is we got to convert this into a heap. We've got a few ways we could do this. First is we could build a min heap versus a max heap. The second option is we could build the heap from the root down or build the heap from the leaves up. As it turns out, the optimal strategy is going to be to use the max heap instead of the min heap, and to use a bottom-up heapification instead of a top-down heapification. Now, the reasons for this are a bit complicated. In effect, the reason why we need the max heap, actually, can someone provide a reason for that?
the reason is because you're adding assuming you're adding your elements, your sorted array to the same array that you're storing the heap in, you want to just be able to add in the element at the end without having to like move stuff around. If you did the min heap and then added the smallest element at the end, then when you added the second smallest element, you'd have to move the smallest element down one and then move that one there, and that would just be less efficient. Whereas the max heap, you just add it to the one to the left.
Yeah. If you think about how the max heap works, we're just shrinking the max heap to the right, and that's how the heap naturally wants to shrink. Whereas if we were trying to add the minimize, then we need to shrink it to the left, and that's not really how the heap naturally wants to do it. Now, you could do it with a min heap that shrinks down to the right, and then reverse the order at the very end, but that adds an extra theta n step. It's just less efficient. We're going to prefer the max heap. The second approach, top-down heapification versus bottom-up heapification, that one's actually really interesting to see. The reason kind of why that happens is that it ends up being asymptotically faster to do a bottom-up heapification than it is to do a top-down heapification. The math behind that is a bit complicated. Talk to me after class if you're curious. But in effect, the top-down heapification takes n log n time, whereas the bottom-up heapification takes only n time to run, if I remember my math correctly. So let's see how this works. We're going to bottom-up heapify the input array first, and I'm going to just show how this is going to work. Now, first off, this is not a heap. It is not currently a heap. Can anyone tell me one example of where it's not a heap? The 2? Yeah, the 2 here, it's connected to 26 and 41. The 2 needs to be greater than these 2. So what we're going to do is we're going to sync nodes in reverse level order. So we'll start off with the 17, and we'll sync it as far as it needs to go. Does it do anything? No. So the 17 is safe, it doesn't move. We'll say that from now on, this is actually a heap itself. The 17 by itself constitutes a valid heap. Next, we do the 17. Does the 17 do anything? No. What next? 41? 41 does anything? Nope. These are all valid heaps of themselves, just tiny heaps. 26? Nope. 19? Nope. 17? 17 doesn't do anything because when we sync, we see that they're both less than or equal to. But what we can say is that this thing itself is now a valid heap. Why is this true? Why can we say that now this 17 component is a valid heap? Yeah.
If you're not able to, so we already determined that recursively, we know that we've already determined that all of its children are valid heaps. And then if the root is greater than or equal to its children, and its children are the roots of valid heaps, then you can, I mean, logically, you can then just say that you can define the whole thing as a valid heap.
Yeah, the left child and the right child, we already proved that they were valid heaps. And now we've just added one new item. We've sunk it as far as it can go. That's guaranteed to turn this into a heap. If you imagine a regular heap, we can always take the root, sink it down, and now we're back to a regular heap. Even when we took the original root, removed it, and added a completely random item to the top. So yeah, this 17 part is now a valid heap. We then take the 2 part. What do we do with the 2? Swap? Swap with which one? 41, yes. Because the 41 is bigger, we need to make sure that this forms a valid heap. And now this part is a valid heap. What do you do next? 15? Yeah, what do we do? Swap with the 19. So now we have 2 valid heaps here. And then what next? 32, swap with what? 41. So now we have a fully valid heap. And now, since the tree rooted at 0 is the root of a valid heap, that means the entire array is now a valid heap. So using this, we have successfully bottom-up heapified the input array. And this would end up taking theta n time total. So now that we've bottom-up heapified the input array, what do we do next? Pop one out, 41. Where do we put it? Yeah, we swap it with the 17, and then we sync the 17 down. Then 32, swap with the 17, sync it down. 26. Yeah. We swap it out, we keep going, and then we just keep going all the way to the end. So what do you think the runtime is going to be for this? What's the runtime for the in-place heap sort? I've kind of already spoiled it a few times, but can you explain to me why that's true? Let's take a minute or so to do this.
Or I guess the only thing that's different is that creating, actually no, the creating is sorry. Yeah, no, yeah. Wait, what do you mean? No, it's the other options. Oh, yeah. Well, I mean, what? Well, yeah, it should be faster. If you listen to like 10 the quintillions for n, then n log n will just be 10 and n will just be like and then it will just be yeah. Let me erase it. Basically.
All right, let's bring everyone back. How many people say it's O of n? O of n log n? O of n squared? Well, it is still true it's O of n squared, because it is an upper bound. N squared is definitely bigger than n log n. But yeah, the intended answer here is n log n. With the information that we have in this class so far, we can show this n log n. Why is it n log n? Yeah.
You have like the heap operations, which are long when we heap with n time because you have to
yeah, you're doing n remove or sinks, and each sink takes at most log n time. So you have a total of n log n as an upper bound. This is actually not a tight upper bound. You can show that heap sort is O of n log n. In fact, we can show a few more things. First off, that heap sort is going to be theta n log n in the worst case. And also that this bottom-up heapification takes theta n time total. But those are a bit trickier to prove. What about the memory use? How much memory does this in-place heap sort take? How many people say it's theta 1? Theta log n? Theta n? Theta n log n? Theta n squared? All right. Yeah, it's theta 1 because we've used basically no extra memory. The only real memory that we needed to use was just a constant number of instance variables. We might have needed a size variable, a counter variable to know where we are, a few things like that. Now, if we use recursion to implement the various heap operations, then the space complexity is going to end up being theta log n, because the sorting, or because the remove operation is going to have log n layers of a call stack. But the difference between those two is effectively nothing, and you can get rid of that by using using an iterative approach to using your heap operations. The difference between these two is effectively nothing, though. It's way worse to be n compared to log n than it is log n compared to 1. Because even if you have a billion items, log n is just 30. So here is a list of the sorts that we have so far. Unfortunately, there is some issues with heap sort. Once you get into 61C, we'll talk about caches. And what caches effectively do is they make it so that adjacent memory accesses are really fast, while also making non-adjacent memory accesses really slow. Or rather, they end up causing that to be slow. Or they end up showing that that's slow because in reality, modern memory systems are really, really big, and it takes a long time to go to a random location of memory, much faster to go to close by areas. Heap sort actually jumps around a lot, so it ends up being really inefficient with the cache. So you end up getting a huge, like 50 times multiplier to your speed compared to, for example, merge sort. So it is kind of bad, but not too bad. Yeah.
Does merge sort also have that same caching problem?
Does merge sort also have that same caching problem? We won't cover this in this class, but as it turns out, no. merge sort is actually somewhat cache optimal. You can actually prove that merge sort is cache optimal for any caching system that exists over any sorting algorithm. I don't know how to prove that. I just read this online, so I'm not sure exactly why. But yeah, it is cache optimal. All right. Now I have 1 minute left. I could go over the merge, like just the merge operation for merge sort, or we could just finish lecture early. What do you all think?
Merge operator.
Merge operator? How, how many people say merge operator? How many people say finish early? Okay, finish early wins. All right. We'll go into merge sort in more detail tomorrow then.